a very brief example. So given some initial word translation probabilities, we can compute the probability of alignments. And so over all of the possible alignments, we can figure out the probability of those alignments. And then given the probability of those alignments, we can compute up the expected counts. So we can compute up what is the probability of the alignments where the was aligned with la. And we can compute that up, summing over all alignments, to create counts for how many times the aligned with la. And then we can normalize those to create probabilities. This means that what we need to do is compute the probability of an alignment given a complete English foreign sentence pair. And if you remember what we talked about at the very beginning of the class, this is just an application of the chain rule. Model 1 tells us what is the probability of an English sentence and alignment given a foreign string, and so we just need to compute the probability of an English string given a foreign string in order to complete that equation, and this is just a marginalization. We marginalize out over all of the alignments. So what's an alignment? An alignment is for every position on the English sentence, we're aligned with one of the foreign words. So we sum over all of the possible alignments that we could get, and then we can compute the probability of that specific alignment and the English sentence that we observed. And so what's the probability of an English sentence and alignment given a foreign sentence? This is just the definition of Model 1, so we plug in that. And so now we've substituted everything in, now we need to simplify it. So this is the same expression. And now what we can notice is that the probability of alignments is constant. So we can just move that to the left, outside of the sums. But then we still have these messy sums and then a product. And so we need a algebra trick in order to handle this. And what we can do is we can turn the sum over products into a product over sums. And this makes it a lot simpler. So why can we do this? We can take a look at one example of this, where we just have two words in our sentences. And this is just applying some basic algebra. So we take a bunch of sums of products, and then we can factorize them out into two products of sums. And so combining the definition of Model 1 with the marginalized probability of the English sentence, we now can get this, and a lot of stuff cancels. So the probability of an alignment is just this, proportional to the probability of those translations given that alignment. And so now what we have to do is collect the counts. And so to collect the number of times that word E, so this isn't in bold, so notice the distinction between the non-bold and the bold stuff. So a single word E in English being translated from a single word F in the foreign language, given the English sentence E and the foreign sentence F. To compute that, we sum over all of the possible alignments, multiply the probability of that alignment given that sentence, times the number of times the English word E was aligned with the foreign word F in that alignment. And then you can apply the same trick before, and it simplifies very nicely. So the expected number of counts of translating English word E from foreign word F is just this bottom equation. So now we can put this together into a maximum likelihood probability estimate, and then we can get the probability of translating English word E from foreign word F, just summing over all of the sentences in the corpus. So this gives us an algorithm. We begin by initializing our counts to 0, form a normalizer, then we can compute up the expected counts, and also compute the total number of times that we saw any particular foreign word. We'll need both of these to compute our maximum likelihood estimate, and after we've computed expected counts over all of our sentences, we can form those maximum likelihood counts, and then this gives us our word translation probabilities again. we go back through with these new parameter estimates and recompute the counts, and we keep doing that until our probabilities stop changing. So here's an example of what happens on a very small corpus. If you have these sentences and you start with uniform translation probabilities, after one iteration they get fairly peaky, and then they get peakier and peakier until you finally get the right answer. The problem with these lexical translation models is that they often get tripped up by selectional preferences. And so, for example, klein can be translated as either small or little. But in some phrases, you prefer one over the other. So, for example, small step is far more popular than little step in English. And so how do we know which to prefer? We can use a language model, and we can combine the language model score with our translation probabilities. And this is just an application of Bayes' rule. We want to find the best English sentence that comes from a foreign sentence. And so what we need to do is we need to compute the maximum English sentence that maximizes the combination of the English sentence and the probability of an English sentence we assume comes from a language model. And then we use our translation score to compute the probability of the English sentence being the translation of the foreign sentence. And the way that this was originally presented is as a noisy channel model. So you pretend that every sentence originally began as an English sentence that came from some language model, and then it was put through a noisy channel, translated into another language, and then you receive this garbled foreign string. And so what you need to do is decode the foreign string into what the original English sentence was. So this is why you combine the language model with the translation model. Okay, so that's IBM Model 1, but what has come after that? Models 2 through 5 become much more complex. We won't go into the details, the book talks about them a little bit, but IBM Model 1 is the only one that has a global maximum. It's the only problem that's convex. And for higher order models, you need to do more complicated machine learning techniques. IBM models have a historical importance that's hard to overstate. And it introduced important concepts like statistical models of translations, generative models, EM training, reordering methods. They're not used much anymore, but they still form the foundation of all of the statistical translation models that came after. And they're still in common use for the task of word alignment, which is an important pre-processing step for just about every machine translation algorithm that is used popularly today. So why aren't these word models used as much anymore? So here are some examples. So take a look at this sentence. Michael geht davon aus, dass im Haus bleibt. And so what happens in this sentence is that you have the German phrase geht davon aus being translated into one English word. And so if you have a word-based model, you're going to lose some of that intuition that assumes is associated with all three of these German words when they appear in one contiguous span. And the IBM models really depend on this word alignment. And in some cases, it's very hard to align English words with German words. So for example, John wohnt hier nicht, it's hard to align does with any of those words. This becomes an even bigger problem when you're dealing with things like idioms. So, John biss im Glas, that literally means John bit the grass. But figuratively, it means that John died. And then you have this English idiom on the other side, John kicked the bucket. And if you literally align these words, you'd have that glass is being aligned with bucket. And obviously, that isn't a good translation. These things only make sense when you consider these as whole phrases in translating the entire idiom. And so this is what later models do. And if you want to find out more about this, please take the next sequence of computational linguistics, where you'll talk about some of these phrase-based models for machine translation. Okay, so to wrap up, we talked about lexical translation, in particular IBM Model 1, and how you can use the expectation maximization algorithm to find alignments that best explain parallel text. So in class, we'll work through some examples to get you ready for the homework, which will be to create an IBM Model 1 translation algorithm.